All right, the squeeze theorem says that if I have these two functions that are squeezing this middle function, if I know these two outside functions are both going to some number, the only way that's going to be possible is if the middle the middle function is also going to the same thing. So really, when you're doing things with the squeeze theorem, you check the two outside ones, and the middle has to be the same. So if I want to find the limit at -1 for this middle function, I check the two outside functions. So if I check g of -1, that means I'm plugging -1 in here. And that's 5 minus 1 is 4. So it looks like that might be the option, but I also have to check h. So I'm doing the same thing, plugging -1 into h. 1/2 minus 1, 13/2. The 1/2 plus the 13/2 is going to be 7, minus 1 is 6. So g of 1 is 4, h of -1 is 6, and that doesn't give me enough information for the squeeze theorem, because if one's up here at 6 and one's down here at 4, there's still this whole area that this middle function could be in. So it doesn't give me enough information, so D is the right answer. If I had simplified h and gotten 4, then they're both 4, and the only way that's possible, again, is that the middle is also 4. But there's two different answers, so there's this gap, and that means I don't have enough information. All right, these next two have to do with how do you use the squeeze theorem, and the main thing is that cosine and sine are these trig functions. They're always bigger than -1, and they're always less than +1. So I can take x cosine of x. If I replace just the trig part with -1, I'm going to get something that's always smaller. And if I replace just the trig part with +1, I'll get something that's always bigger. And then as these things go to 0, I get 0 in both cases. So as this function goes to 0, I get 0. This function goes to 0, I get 0. But both of those are 0. The middle also has to be 0. So your final answer for that one is 0. 27, same idea. There's a bit more happening with the sine of 1 over x, but it doesn't matter what's inside of a sine function. It is always bigger than -1. So if I replace it with a -1, I get something smaller. It's always smaller than a +1. So if I replace it with a +1, I get something that's always bigger. And again, these two bounding functions are both going to give me 0 for the limit. And since those both become 0, my final answer is that this one also has to be 0. All right, so for these short answer ones, I'm looking for these inequalities, the fact that the two bounding functions go to 0, and then your final answer is also 0. All right, so those are the kind of pieces that would give you all the points for these ones. The inequality, the individual limits, and that gives you the final answer. All right, so that's the squeeze theorem. All right, they're all really similar when you actually use them in practice. And our last learning objective from the Unit 1 test is multiple representations, which is basically equations, graphs, and tables. All right, so these ones are looking for the limit as x approaches 1 is 5. All right, for this rational, we don't care about exactly at 1, so we can ignore the 3. All right. When we look at the limit, we try to plug it into the rational. We can't, so it means we have to factor. The x minus 1's cancel. And then I can plug in 1 plus 4 is 5. All right, so it looks like 1 is going to work. 2, our table, when we exactly plug in 1, we get 5, which doesn't tell us anything about a limit, because the limit is just around 1. So we're looking out here, and we have this big jump from 500 to -500. So this one's limit at 1 does not exist, so 2 is out. And our graph at 1, again, we don't care about exactly at 1, so I don't care about exactly on this blue line. But everywhere around there, we get these values here, which are at 1, 2, 3, 4, 5. So this is also at 5, which means that works. So 1 and 3 are our answers. At 29 is basically taking the table from the graph right, so exactly at -1. All right, this is where we're looking at the exact values of our function f. Exactly at -1, I'm going to get 2. All right, so C and D are out because I know when I plug in -1, I get that dot there at 2. So how do I determine between A and B? Well, every number around -1, like up here and up here, I should be getting numbers close to 3. All right, so A is going to be out because I get this number that's close to -1, but that number is close to 2. So B is the right answer because right at -1, I get 2, just like my graph says. But everywhere else around -1, I get these numbers that are close to 3, just like my graph says. Everything up here should be close to 3, and then just at -1, I jump down to 2. H is a piecewise function. I want the limit to not exist. So the way we check limits existing for piecewise is we check the two sides of the piecewise. So we have to do 12 minus 3. That's 9. 4 times 3 minus 3 is 12 minus 3, which is 9. So the limit does exist at 3 for this function, so that's out. For question 2, again, we don't care about what happens exactly at 3. But on the left-hand side here, 3, 8/3, 7/3, next would be 6/3, which is 2. On the right, 3, 2, 1, the next would be 0. So on one side, everything's going to 0. The other side, everything's going to 2, which means there's a jump. So our limit won't exist. This is actually one of the right answers. And then limit at 3, there's a jump. So that one's also not going to exist. So 2 and 3 are right. All right, create a table on a graph such that the value as x approaches 2 is the same. All right, so this is one of those things where you can be super creative, or you can do it in the simplest way possible. All right, so as x approaches 2 is the same. So if I want my limit to be, let's say I want it to be 1. All right, I could just do a flat line like that. Because when I plug in values close to 2, I'm going to get values close to 1. And then I just need to mimic the same thing with a table. My values need to get close to 2, so I can do like 1.99, 2.01, 2.1. All right, those values are getting close to 2. And I want the y values to be getting close to 1, so it matches this one. So I can just do like 0.99, 1.01. Right. So as my x values get close to 2, my y values get close to 1. As my x values get close to 2, my y values get close to 1. All right, so that's how you can do this. All right, just make sure the table and the graph are saying something similar. All right, so that's all of the Unit 1 test. Again, so go through here, kind of figure out what you were missing when you took your test the first time. And again, the retakes and stuff all have similar types of questions, so they might be slightly different, but the techniques are going to be the same.